Hello everyone, this is Nathan Earnest-Noble again. Thank you for joining. This is going to be Lab 5. In this lab, we're going to be taking some of the concepts from the two lectures that I had given and making some practical implementations of them. So namely, a big thing that we're going to be doing in this lab is taking this idea of quantum process tomography, using it to measure the quality of a gate, and then also sort of showing the impact of readout errors specifically and how this sort of degrades the quality of the QPT results, and then also how you can use readout error mitigation to sort of help improve those results. So with no further ado, let's go ahead and jump in. I really do want to emphasize, just because I personally made the mistake a few times myself, please, when doing any of the exercises for this, there are going to be some things where we include, say, noise model or a seed transpiler or a number of shots. You're going to want to make sure that you include all of those in the execute function. If you include it, there's other ways in principle that you can include this, but it gives some issues when we start to do the grading function and actually being able to get reliable results on the grading. So let's go ahead and jump in. So we're going to be, and then also actually I should say at the end, we're going to sort of do an analogous study of this pulse scaling technique that I had talked about. We're going to do some sort of an analogous study because doing the actual pulse implementation itself is a bit difficult in the sense that not everyone necessarily has the pulse level access to do it. But we'll sort of show in principle how this still works when working at sort of a chasm noise simulation, and we'll get into some similar ideas here at the very least. With no further ado, let's go ahead and jump in. So at the top of this notebook, we've imported, or we have several different functions that we're going to want to import. I'm not going to cover them in detail just because they'll naturally arise as we go throughout the lab. So for your problem, or for the sake of your grading, the first question is really to just reproduce this circuit element here that you see. It may seem familiar to you in that it is very similar to the ZZ Pali feature map. And in particular, it has this sort of CNOT with an RZ and another CNOT. That is the thing that allows us to do this sort of pulse scaling trick that I talked about in my second lecture. For the sake of this lab, I'm actually not going to, or for this lab preview, I'm not going to do this exact same circuit just so that there's some sense of you being able to figure these things out yourself. With that said, one thing I had mentioned in one of my lectures is that there's this idea of the quantum information modules. So here we've imported qiskit.quantuminfo as QI. And I just wanted to sort of touch on how this can be useful when thinking about how you construct that CNOT gate from the cross-resonance-based interaction. So to this end, let's go ahead and start off. So the cross-resonance-based interaction, as we discussed in one of the lectures, is this sort of this ZX type interaction. So here we have this RZX. We're going to do it such that the control, say, is our qubit 1, and then the target is qubit 0. But now in order to actually build up a CNOT, we pointed out that you have to do these additional things where you do a Z rotation on your control and then an X rotation of -pi/2, and you do this on your target. Now, here, this Qiskit information or quantum information dot operator, what this ends up doing is now, if we go ahead and look, so just for the sake of visualization, data, let's go ahead and just run to 3. Here we again need to do some normalization factors. But if you normalize it, here you can see that you effectively have the CNOT unitary from this sort of RZX interaction. Now, for the sake of posterity, let's go ahead and just do this. Target, and let's just say CNOT. So what I'm going to do now is actually just take this target CNOT and do the CX. 1 comma 0. Now here, do something similar. Say target unitary CNOT. Let's target CNOT. And then now here, go ahead and do this. Then take target unitary CNOT. In this case, we don't need to worry about this normalization factor, but now you can, lo and behold, the two matrices end up giving you the same thing where you have your sort of CNOT here and your CNOT here. Now, one thing I had sort of talked about in the lectures is how you can natively build open CNOT, or a CNOT that's controlled on 0 from this cross-resonance interaction by adjusting this negative sign here. The sort of circuit-based approach to do this is to add an X gate before and after your CX. And so now this is sort of target CNOT open, if I were being precise. But just to show it, one thing also we're going to need to do is include an extra global phase factor. Minus sign here. And we do this, and then now lo and behold, here is our target CNOT that is actually the open CNOT, just to draw it so you get a sense of what that looks like. Here is this open, so 0 controlled CNOTs, and then for our RZX based approach, you can see that this is now the sort of circuit that you're implementing. And then in either case, up to some sort of global phase factor and normalizations, you end up getting that sort of 0 controlled CNOT. So I just wanted to take a moment, go back to what we had talked about in one of those lectures and show how you can use this quantum information module to really just construct the unitary that you have using sort of this quantum circuit perspective on things. Now, for the sake of the lab, what I would like to do is instead focus on doing Toffoli gate, or a controlled X gate. So now let's go ahead and just draw that. Index out of range. Yes, I need to, so this is going to require 3 qubits. I draw that. And now here, let's go ahead and just get rid of this. Target unitary. And here now you can see that this ends up being the Toffoli, where it's ones along the diagonal until you get to these last 2, and then you flip that. So this gate here is basically a conditional gate on both Q1 and Q2, where I'm going to flip Q0 only if and only if Q1 and Q2 are both in the 1 state. So this ends up being a useful operation for a variety of different quantum applications. Now, I guess I should say that in principle, actually, when you try and run a Toffoli gate on IBM Quantum Backend, Toffoli gates are not a part of sort of the native interaction for IBM hardware. So you instead have to transpile this to CNOT-based implementations. And then this is actually an area of research where people say try to construct new sorts of gates to do this. Now, ultimately, what we're wanting to do is this essence of quantum process tomography. So this target unitary here, what this is going to be useful for is that as we are simulating our circuit, we want to get an essence of the fidelity of the desired unitary. So what you do is you use this target unitary as sort of the comparison for what you're going to do. So now in this grading function, I'm not going to execute any of these grading functions, but for your stuff, all you will need to do is end up running the quantum circuit that you did in the first box here. So let's go ahead and move on. And now we actually want to do quantum process tomography. So for the quantum process tomography, we want to do it in the context of chasm shot noise only. So eventually we're going to start trying to incorporate back-end noise that's sort of somewhat representative at least of real quantum hardware. But to start, let's just do it with this chasm simulation in which the only source of noise we have is sort of the sampling noise or the shot noise, so the finite number of measurements that you do. So for doing this, this is where this idea of the seed simulator and seed transpiler will become particularly important. To start though, the hint that we provide here is that you have these process tomography circuits. So I love myself the help function. So if we look at quantum process tomography circuits help, what you can see that this takes in is two really important things. So one, it's going to take in the circuit that you want to actually do the process tomography on. So in the case of this preview, it's this Toffoli gate, and in the case of your lab, it'll be this gate, this sort of circuit up here. So now the other thing that it takes in is the set of measured qubits. So let's go ahead and do this. So we're going to say QPT circs equals process tomography circuits. So this is where we have targets. Measured qubits equals, now we're going to be measuring qubits 0, 1, and 2 in the case of this. So now this QPT circs here is going to generate a list of circs, or this process tomography circuits will generate a list of circuits. And if we go ahead and look, here we can see that it's 1,728 circuits in total. So that is going to be the total number of circuits that you actually need to execute process tomography on a 3-qubit system. If instead now you were doing it on a 1-qubit system, this is where from the lab you can see that it's sort of measuring in, you'll have a total of 12 circuits to sort of measure in all 3 bases as well as prepare all 4 of those states that were briefly discussed in the lecture. Now, in your case, you are going to be doing a 2-qubit quantum process tomography. So the number of circuits that you will ideally see is 144 circuits. But moving back to our specific scenario here, we have this. Now, we want to go ahead and import a simulator. So backend, there's different sorts of simulators that you can have. So you could do state vector, which does a nice sort of exact answer, but the thing we're interested in is a chasm simulator. This chasm simulator will be the thing that allows us to eventually include a noise model. So then now, let's just, it's here, so QPT search. So now I actually want to go execute this function. So to do this, I'm going to execute QPT search. Now this is where I need seed simulator equals 3145, seed transpiler equals 3145. And now I will also say QPT result equals QPT job dot result. So if I've run everything, yes, execute. Of course, it will need a backend. So here, that is important. So now that we've run this, we're going to ultimately get the QPT results. So I'll say here that because I'm doing a 3-qubit instance, it has a decent amount more of circuits, and so it's going to take a little bit longer to execute than what you should experience. Ultimately, you should find that your simulations don't take too long, ideally. So now let's go ahead and just show get counts. So if we do this here, you can see for each one of those circuits, you have a different number of shots. Now here I've already sort of realized that one thing I did not do, which you definitely should, is include the number of shots here. So you end up saying shots equals 8192. So now when I add a few more shots, it's going to take a little bit longer to simulate. But here we will go ahead and just let this run for a second. Just while it's running, I'm going to go ahead and pause the recording and we'll see you in just a moment. Great, so I let that run a little bit. And then now just looking at these get counts, you can see that this ends up adding up closer to that or to that 8,192 result, which is what you want to use when doing the exercises for the homework or for the grading aspect of this. So now one thing we will be doing in a bit is actually including a noise model here. But for the time being, let's go ahead and move on. So now what we've done is we've generated those different quantum process tomography circuits that we wish to run in order to actually measure that sort of unitary. But now we actually need to do some extra work. So we've run them, we have the results, and we get the counts, but we want to turn that into an actual, take those counts and turn it into something that can tell us what the quality of our gate ultimately was. Namely, you want to get this idea of this Choi matrix. So to do this, we're going to make use of this process tomography fitter. So in the typical fashion, process tomography fitter, include this I. So here's this help function. So here it's going to take this result from the QPT. And I actually think that that's the only thing that we need to include potentially. Let me just double check. Yeah, I think that that's good. But sometimes actually it is useful to include the circuits. So maybe we'll go ahead and do. So now here we can take quantum process results, this. So now here we can just, let's call it QP tomo equals this. So now this right here is going to be the thing that actually starts to take and process those results. Ultimately, we want to do a fit. So let's just say we do least squares. So here I believe we specify you're going to use this process tomography.fit. So in order to do that, we have different methods that you can use. So for the case of grading functions, let's go ahead and make sure that we use this least square. So now when you do this fit, this ultimately will take the quantum process tomography results and fit to it in order to actually give you that Choi matrix. Now it is that Choi matrix that is basically describing what the experimentally implemented unitary is. Now, what you want to do is compare, so that would be actually quite sufficient to get a sense of what the unitary is, and you can look at the sort of PTM matrix it's called for this. But for the sake of the homework or for the grading functions, what we actually want to look into is what the corresponding fidelity is. And this gets back to making use of that target unitary that I had mentioned earlier. So here we're just going to say fidelity equals, so here in the hint, you can see that we have this average gate fidelity function. So this is built into the Qiskit information. So perhaps actually I will let these run, then insert extra cell above just while it's running. So I can do this and say help qi dot average 18. So again, these results will take a little bit longer for my simulations to converge because I'm doing this 3-qubit instance. So I'll go ahead and pause and we'll be back in just a moment. Great, so we let this run. This took a little bit to run, but then now we get to this, this help function of the quantum information average gate fidelity. Here you can see that it takes in the channels, so this is going to be the sort of fitted Choi matrix that you have here, and then the target unitary. There's some other aspects here that we can get into if you are interested. I'm happy to answer. But so now let's go ahead and say fidelity equals qi dot average gate fidelity. We're going to take the QPT least squares fit. And then now we're also going to take the target unitary that we have above. And then now from this is going to take that sort of multiply the sort of two matrices where you have your sort of experimentally measured one and then the inverse of your target one. And then from this, take the trace of that, and then ultimately this should give you your fidelity. So we run that. We can see that this actually goes quite quick. So in the case, we're very close to 1, which is sort of a perfect fidelity. It's not exactly 1, and this is just, say, limited to some sense of finite sampling that you're getting from the shot noise here. So now we've done the quantum process tomography for, in my case, the Foley gates, and we've done it with shock noise only. But we actually want to try and include some sort of realistic noise models for a backend, or at least something that partially captures noise of a backend. So a big aspect of this, as we talked about in one of the lectures, is this idea of T1 and T2. So for that, we're going to build sort of a very basic noise model in which we include the T1 and T2 noise, so sort of coherent noise. So we're not going to be building a noise model that includes, say, coherent errors or crosstalk. There is a very rich field of study in sort of building up more and more accurate noise models. So perhaps I can point you in the chat to some of the tutorials where you can start to do this. But for the sake of this lab, we're going to just really focus on sort of essential aspect of sort of quantum information, in that we have these T1s and T2s, which are finite in their lifetime. So for this, I say have 4 different values here. So it's say corresponding to a 4-qubit instance. I think really it should only matter that you have 2. So just make sure that you end up using the first 2 in this list here for the actual comparison. But then you, for your own interest, can run and see how these T1 and T2 values impact things. So I just wanted to walk through these. So right here, the units of my T1 will sort of be relative to the characteristic gate times. So in this case, I've put everything in units of nanoseconds, where the T1s and T2s then are, say, on the order of microseconds. So for this one, I say have a 15 microsecond T1. For my T2, in the case of this qubit, I end up making it T1 limited. So the best T2 that one can hope to have is twice T1. So then in that case, this is, say, a 30 microsecond T1. For the next qubit, I have a T1, or sorry, a 30 microsecond T2. For the next qubit, I have a 19 microsecond T1, and then a T2 of 25 microseconds. For the third, so it's not quite T1 limited here, but it's a little bit better. Then say for the third qubit, I end up having 22 microseconds, but my T2 ends up being a little bit lower than my T1 at around 18 microseconds. And then lastly, I finish off with another T1 limited device of, say, 14 microseconds and 28 microseconds. So all these, say, are somewhat realistic values. You can end up measuring and seeing that many of our qubits actually end up having T1 values and T2 values that are on the order of 100 microseconds, so quite high. And these fixed frequency transmon qubits really help to that end. But one thing that I want to emphasize is that these T1s and T2s are something that fluctuate over time because they're highly sensitive to the environment and what have you. So because of this, the various things that we're showing here will be something that you'll want to keep in mind aren't always a constant. So namely, I want to run we're going to be going into this idea of readout error mitigation. Well, you can make this matrix, but if you make it at one time, it's not necessarily going to be useful to use that same matrix at a later time. And this is something that you should keep in mind when running your experiments, is that there are system fluctuations, and this is something that you have to take into account as you're trying to sort of run experiments and use error mitigation techniques, and the fact that these things are somewhat unstable. Looking at the different gate times, so the time for my U1, so this is the characteristic time that it takes my RZ gate to actually run. So as we said in one of the lectures, the RZ gate is this virtual gate. It happens instantaneously. So we're going to take the time there as being 0. The U2, so this ends up being, say, a pi/2 pulse, so how long it takes to sort of pulse to the equator. Typical calibrations for our backends now end up being around 36 nanoseconds. That said, it doesn't have to necessarily be that way. So some recent updates in how we calibrate things has actually reduced that. This also goes to say that the fastest single qubit time that I've seen within sort of a fixed frequency transmon perspective is around 5 nanoseconds. This is coming from some of our colleagues out in Zurich who did some research trying to make sort of beyond drag pulse gates. So 50 nanoseconds is a bit on the longer end, but let's just keep it for this for the sake of this lab. Then U3, so this now is the concatenation of sort of two U2 gates with the U1 gate in between, and it's this U3 that does the sort of arbitrary single qubit state preparation. And so two of those, so it end up in duration being twice of whatever it takes for your U2 gate. The CX gate, so this gets into large area of research, as I've mentioned, I believe, in one of the lectures, in which people are trying to really push down the speed of the 2 qubit gate that's based on the cross-resonance interaction. 300 nanoseconds is, say, a decent speed for the 2 qubit gate on IBM backends. It's by no means the fastest, so this is where, say, doing the direct CX gate is something that sort of allows you to be on the order of just a little over 100 nanoseconds in the total duration of that gate. But for the sake of this lab, we'll keep this fixed at 300 nanoseconds. Now, in this exploratory question that comes at the very end, this is where we actually will talk about the analogy of the pulse scaling technique. And what we'll do is scale the characteristic time of the CX just for simplicity in the simulations. What actually happens on the back end is that you're not implementing a CX gate, you're implementing some RZX type gate. So it's just an analogous study, but I think it'll get across the point. Then you say have your time measure and time reset. So 1 microsecond, say, is going to be a relatively typical time for measurements on our backends. And then what I'll show you in a second is it is the duration of this measurement time that will really impact a lot of our measurement pulses, or our readout errors, excuse me. So for now, let's go ahead and fix that. So then from the error component of Qiskit, we have these two different things that we're going to import. So namely noise models. So this is going to be the thing that actually allows us to build a noise model, as well as this essence of thermal relaxation error. So this is going to be the sort of decoherent error for T1 and T2 that we build in. So it's sort of a minimally viable sort of thing that you can do for your noise simulation. So now, here in the case of your notebook and your grading, you'll want to make sure that you include sort of error channels, or that you add errors for each one of these gates. For the sake of this lab, I'm just going to go ahead and do two things. I'm going to add the errors for the CX and add errors for the measure. So I'll go ahead and leave it to you to ensure that you add it for U1, U2, U3, as well as this reset. So for this, this is where we're going to say noise thermal equals model. So this now is just going to be creating an instance of a noise model. By the way, if you want to sort of look at some tutorials that exist, please check out the Building Noise Models tutorial that's in Qiskit. Specifically, they have a T1 and T2, and they'll be very helpful in guiding you here. So then now noise thermal. So we want to then say for J in range. So for you, it will only be important to do it for 2, because I'm doing it for the Toffoli gate. I need to do it for 3. And then if you want, you can say do it for all of them in the range of 4. So it doesn't actually hurt. And actually, I think for the grading functions, you should do all the way in the range of 4 to include it for all 4 qubits. But then now we can say noise thermal dot add quantum error. And then this is where I want to add the error. I think it's called, yes. This is J. Here we say measure, say J. And now for J in the range 4, this now is where I want to add the so errors. X. This is J. It's okay. Say CX. There's J, K. Okie dokes. I, of course, made some errors here. Thermal relaxation error. Did I not import this? It would be useful to import that, wouldn't it? So hopefully I run this. Error measure, K, measure. Whew. All right, cool. Got it. So now we can go ahead and look at this and then just say noise thermal. And here you can see now that we've included, we've included different noise channels or noises for the CX and for the measure. As I said just a moment ago, make sure you include it for all of yours. So in your case, you might want to go in here and say noise thermal errors U1, say something like U1. Here, go ahead and leave that the same. So you can do this and then curious as to why it's not adding U1 here. Just want, it's not important right now. Let's go ahead and do this. We can come back or I can answer any questions that you may have. But ultimately, when you're looking at noise thermal, you should make sure that you're seeing errors for all of them. So now let's go ahead and look at this. So here for your grading function, you're just going to end up taking this sort of noise thermal model that you've built, and it'll compare, and hopefully you end up seeing that you get the right thing. So what we now want to do, though, is we want to take the same quantum process tomography circuits that we ran before, but we're going to run them using this sort of simplistic T1 and T2 type noise model. So to that end, we can take much of the same stuff that we had before. So don't need the simulator again. We don't need the same circuits. We've already generated that. So now here I'm going to call this noisy QPT job. And this is where I want to include noise model equals noise thermal. And noisy QPT result is that. But now ultimately for this, we're actually just going to go straight to measuring the fidelity. So then this now is where I come here. Let's go ahead and take this. Okay. So then now go back down. So we're going to take the noisy QPT result. We're going to call this noisy QPT terminal. Still going to do the least squares fitting. Noisy QPT least squares. Say noisy fidelity. So if I run this, so this will take a bit longer, and especially now that we've included this noise model, it's going to be a bit slower than when you do just the CASM simulation. So I'm going to go ahead and pause, and we'll be back as soon as it's done. Okay, so now we've let it finish, and we can see the noisy fidelity result is around 88%. Just to put the two things side by side, so we can say print fidelity and then noisy fidelity as well. And so you can see that you get effectively a perfect fidelity when you just do this CASM simulation, but once you include this readout noise, you end up being sort of brought down by 88%. Now keep in mind, you're implementing the same unitary, it's just that your measurement errors have gotten pretty bad. Or you haven't actually corrected for your measurement errors. I just really want to sort of drive this home real quick. So you don't necessarily want to do this for the purpose of your lab, But if I say increase the duration of my readout pulse here to say be 20 microseconds, much longer than what we actually need, I'm going to go ahead and simulate this. So now I've built this noise model with the sort of characteristic measure time of being 20 microseconds instead. So now I'm going to go ahead and run the same thing. Will take a little bit of time to process, but I will be back in just a moment. And what we'll see here is that this noisy fidelity value ends up being much lower than in the instance when you had, say, a 1 microsecond readout pulse. See you in a moment. Okay, so now we can see that when we took that 20 microsecond readout time that we sort of put up here, the corresponding noisy fidelity is much worse. It's now around 20%. So you can see how being careful both in tuning up your readout pulse to sort of be on the shorter side, but not so short that you can still resolve your 0 centroid and your 1 centroid well, as well as sort of correcting for the readout errors that exist regardless. So for the rest of this, I wish to go back to this sort of 1 microsecond type regime. So we'll go ahead and run that. While that's starting to build out, one thing I will just start to set up is now we have this idea of the readout error mitigation that we actually want to do. So for that, we're going to be making use of some built-in functions into Qiskit, namely this A matrix that I had mentioned, and it comes in through this sort of complete mesh cal function here. So I will say that readout error mitigation is something that there are a wide variety of ways that you can do it. So as I sort of mentioned in the lecture, you can do it with this idea of an excited state promoted readout. So namely, the transmon qubits have more than just 2 energy levels. They have higher ones as well. So if you put it up to a higher energy level, then it takes longer for it to sort of decohere, and then so you don't end up getting those sort of readout errors where it decays during your readout process as much. Or if it decays, it's decaying from, say, the 2 state down to the 1 state, and then you'll still be able to classify that as being a sort of 1 state type result. So I want to sort of use the help function as I tend to do, where you say help complete mesh cal. But while the other thing is sort of running again, we're going to take a pause and I'll be right back. Great, so we ran it. We can see now that we're sort of back at this 88% value. And then now looking at this complete mesh cals, what is convenient about this is that it only really needs to take in the qubit list that you wish to measure. And then in addition to that, it returns 2 things, I believe. It returns the sort of set of circuits that you need in order to actually do the measuring calibration, as well as the state labels. So let's go ahead and do this, where we say mesh cal circs state labels here. Say that takes in qubit list equals 0.1. So nice, that ran. So then we can take a look at mesh cal circs. Here there's 4 circuits because it's only 2 qubits, but if you say at this, you can see now that you end up having, say, 32 qubits. So in the context, so this is where it's sort of that exponential scaling to do the complete matrix here for your readout matrix. This is not the ideal thing, and this is also maybe where you want to try and do readout. In the ideal sense, it might be nice to do readout error mitigation in a way that doesn't really depend on, in this sort of exponential sense, on the number of qubits that you're trying to mitigate. Or at the very least, you can sort of do a tensored version of this where you're only doing subgroups of the qubits. For the case of our problem, we're going to need 8 circuits for doing readout error mitigation, a complete one on 0, 1, and 2 qubits. Just to give you a sense of what this looks like, we can look at each one of these circuits here. draw. And we can see the first one just takes all the qubits, prepares them in the ground state by doing nothing, and then measures. And then say this last one here, you put all the qubits in the excited state and then measure. And then from this, you're going to see how much decay you say have in the readout process. So this will be the readout sort of errors. And then this version right here would say be the state preparation errors. So now we want to go ahead and use this. Then so now mesh cal job equals execute. So then now here's where we want to make sure that we use simulator. So here we're going to use the seed simulator, seed transpiler shots, as well as the noise model in this case, because if you don't actually use the same sort of noise model, then you're not actually going to properly do readout error mitigation. So then now here's this. Okay, so then we can say mesh cal result equals mesh result. So then now this will end up being the thing that gives us the sort of results from doing that noisy simulation, but in a similar fashion to the quantum process tomography, we actually need to fit this in some way. So this is where we're going to make use of this complete mesh fitter. So perhaps I can do this. These run much faster. There's only 4 circuits instead of this 1700 that we had earlier. So we can say help. Fitter. Mesh fitter. So it's a slight error, but if you click on this, you would ultimately see that it's complete mesh fitter. So then now here, what we can see is that it's going to take in the results object from the measurements cals, as well as these state labels here. So here we can, let's just call it mesh fitter equals this. Cal results. State labels. Now here we're going to actually create the filter, it's sort of called, in order to that should run. Nice. So now one thing I want to say, so here we've actually done the fit. So we can go and take a look and we can see mesh fitter dot plot. So this is for a 3-qubit instance, and now here you can sort of see the along the top we have the prepared states, and then you have the sort of measured results. So you can see that when you prepare 000, you measure complete 000. So there's no sort of initialization errors, so you don't accidentally end up having your qubit get excited to the one state during the measurement process. But then looking at the other end of this, say if you prepare 111, you can see that there's some slight amount of decay into the lower states. Just to really emphasize this earlier. So here, just because the noise model works very efficiently for the measurement stuff, here you can see that the decay ends up being a bit greater in this case for these other values here. But this is a distraction. So maybe not something I should do, but something I would definitely encourage you to play around with and see how these different things impact stuff. But so let's stay focused here. We're going to take this. So now we have this. But now ultimately we want to take those noisy results from our quantum process tomography up here. So here we go. Here's this. Let's go back. Let's do this. So now we want to take the filter and let's do it this way. Apply that filter to the noisy result here. And so we can say emit noisy QPT results. Is this? Let me just. So applying it takes a little bit, but I'm not getting an immediate error, so that's good. So then now, here we then want to go through. Just do this. So mitigated noisy QPT tomo, you're going to fit to this. We're going to keep the same process tomography circuits. So then now this, we actually do the fit, submit. This, we're going to compare it to the same target unitary. Mitigated, mitigated. Now we'll go ahead and run this. I'll pause this just so that we don't wait for the duration of this. Great, and so now we let that run. We've applied the readout error mitigation, and you can see, lo and behold, the fidelity is a bit higher now. So let's just go ahead and print each one of these up next to each other. First one, we're just going to print the fidelity. The second one, the unmitigated noisy fidelity. So you can see you start off around 99%. You drop down to around 89% due to the readout error specifically. And then after you do some readout error mitigation, you get back up to, say, 98 or close to 99%. Not exactly the same because we did include some errors for our CX gates, which will definitely sort of help bring this fidelity down a bit. So then this is sort of the conclusion of the main component of the lab. Now I sort of want to move into this exploratory type question where we actually, through this analogous study of scaling the duration of our gates, can show how this pulse scaling technique can help improve the fidelity for different sorts of RZs or RZs of different thetas, controlled RZs of different thetas more so. For this, I actually want to move back to this instance of this initial problem here so that the scaling can, even though it's analogous, at least have some sense in sort of what's going on. So for this, I'm going to just take a moment, build that up, and then we'll be right back. Okay, great. So I made this sort of helper function, which I'm just calling scale RZZ. So this is just taking that quantum circuit that's this ZZ Pali feature map and sort of implementing different versions of it. So if I take pi over 2, it ends up having sort of a RZ or a virtual Z gate of pi over 2 here with the two CXs, and just really emphasizing it's the CX with this and the other CX, which is at least one of the things that we can sort of scale in a nice efficient manner and do this pulse efficient transpilation. So for the analogous study, what we're going to sort of do is instead just say take the characteristic duration of these CXs and sort of reduce that duration. Again, keeping in mind that what actually happens is that you don't implement a full sort of CNOT because that's actually more than what you need. You sort of do that ZX of theta only. But you can get across the point here by doing this. And then now we're going to sort of scale it, say from the duration of these, say from being 50 nanoseconds up to 400 nanoseconds, and we'll just do it for 5 points. And then so now it is this that then, sure. So yes, the time CXs will sort of be equivalent, say, to how much of that RZ theta you actually wanted to do in this analogy. And we're going to go ahead and keep our time fixed at 1 microsecond, our measurement time. But then everything else that's in here is effectively as you had seen it before. So we had the error measure, the error CX. I don't actually include the U1 or the various single qubit gate errors or the initialization error. And then here actually we should make sure that we do the execute with the noise models. So here this is where you say noise model equals thermal. And then now ultimately this should be the same idea. So we're going to go ahead and run it. Of course, I'm getting some errors. Simulator noisy. That's because we just do simulator. I'll go ahead and gives me another error because I still have simulator noisy elsewhere. Bum, bum, bum. See noisy. So this will take just a little bit. It is a bit faster, you can see now, just simply because we're not running into as many of the issues with 3 qubits. Let's see. So it seems that I might not have done my readout error mitigation. Give me a moment as I... Okay, and as my quintessential bug, I forgot to include in the execute here for the mezcal jobs, the noise thermal. So this is why it wasn't actually applying the readout error mitigation in the way that one would hope or expect. But so I've run this through for the various different durations, just to be a little belaboring here. So we take the quantum process tomography circuits for the target unitary, which is instead now this circuit here. What we're going to sort of find is that the target unitary will adjust depending on what your sort of desired theta is. Then you take your quantum process noisy results. So you're going to simulate those circuits with the noise model built in, doing all these things the same. Then here you end up having your results. Then after that, we're going to run our readout error mitigation circuits, again with the noisy results, fitting that. And then we do 2 different things here. One, we apply the readout error mitigation and then do the fit for that. So you have the mitigated noisy fidelity. And then also you just do it on the initial results without doing the readout error mitigation. And then now you have the unmitigated noisy fidelity. Then you get that, and then you plot it for these 2 different values. And then lo and behold, you can see that sort of the characteristic duration, or what's equivalent, say, to the theta that you're trying to get in your RZX type gate, ends up sort of the longer it is, the lower your fidelity will be. And this is sort of analogous to what we see in the pulse efficient implementation when we do it with real hardware. So this is the conclusion of the lab. I hope that you got some useful knowledge from this. If I were to really emphasize some things, it's to point out, hey, make sure that you consider different sort of error mitigation techniques that you can use to improve the results of your real hardware runs, keeping in mind that your real hardware is a system that fluctuates over time. So you want to make sure that you keep that in mind when trying to apply different error mitigation techniques, whether it be, say, this readout error mitigation, or there's other things like Richardson extrapolation and what have you. With that said, thank you very much. I will be in the chat answering any questions that I can. Talk to you then. Bye.